We now know that in order to have incremental power gain, we need to have a nonlinear two-port. What we will now do is look at the nonlinear two-port, specifically its incremental linear equivalent, and establish the conditions for maximizing the gain. Okay. So far we have talked about power gain, but for simplicity here I will consider voltage gain, but you will easily see that maximizing this the way I do it also maximizes the power gain. Okay. Let's assume that we have a 3-terminal nonlinear two-port for simplicity. And we have the port 1 voltage and port 1 current, port 2 voltage and port 2 current. The nonlinearity is given by currents as functions of voltages. Like I said earlier, other representations are possible. Okay. Now let's also say that there is some operating point. We will later worry about what exactly the operating point is that we must choose. Okay. So at the operating point we have the port 1 and port 2 currents. Now if we take the incremental equivalent circuit around the operating point, what do we have? We know that it is going to be a linear two-port, and because we have here currents as functions of voltages, in this case we will have Y parameter description. Okay. And the port 1 and port 2 incremental voltages and currents are given here. Okay. This and that and that and that all are incremental quantities. What is it that we do? We connect a source, a signal source to port 1 of this incremental equivalent and a load to port 2 of this incremental equivalent and evaluate the gain. Okay. This is still the incremental equivalent. We will get some constraints for maximizing the gain. Then we look at those constraints and see what it implies for the large signal, the total characteristics F1 and F2 of the nonlinear two-port. Okay. So we will now assume that we have a signal source Vs with a resistance Rs. This is the representation of any source. Okay. Signals can come from some sensors, let's say the microphone into which I am speaking, and it can be from some other stage, let's say another amplifier's output, or it can be anything. Okay. The bottom line is it always can be in general represented by a voltage source in series with a resistance. Okay. Now we connect that to a linear two-port, which we know is the incremental equivalent of the nonlinear two-port. Okay. because we have already established that we need a nonlinear two-port to have incremental power gain. Okay, so this is the incremental equivalent of a nonlinear two-port. We will later see when we go to the specific device how to come up with a circuit which has this as the incremental equivalent. We will somehow assume that the incremental equivalent of our circuit is such that the signal source is connected to port 1 and the load is connected to port 2. Okay, so this part is pretty simple. Now, we have to solve for the output voltage V0, which you see is exactly the same as this V2. Okay. So essentially we have to solve for V2. So first of all, we have relationships imposed by the two-port. Okay, this must be familiar to you from regular circuit analysis. Every element in the circuit imposes some constraints between its voltages and currents, and you take all of the constraints and solve for the circuit. So this nonlinear two-port, by the way, I could also draw the small signal equivalent of this using conductances and control sources, that is the circuit equivalent of the Y parameters. So it will be the same thing. Y11 V1 plus Y12 V2, and I2 will be Y21 V1 plus Y22 V2. Okay. In addition to this, we have a relationship from this side. We know that the voltage across this resistor is Vs minus V1. Okay. That is, here we have Vs minus V1. So the current through this, which is equal to I1, has to be Vs minus V1 times 1 by Rs or Gs, which is the conductance. Okay. And on this side, I2 is the current flowing in RL, but from bottom to top. Okay. So this imposes a constraint between its voltage, which is V2, and its current, which is I2. Okay. So what do we have? I2 will be equal to minus GL times V2. Okay. This comes about because I2 is flowing in the upward direction. Okay. So now we have these 4 equations, and we have 4 variables. So we have to solve for I1, V1, I2 and V2. Okay. And specifically it's V2 that we are interested in. We have to find a relationship between V2 and the source voltage Vs. Okay. So at this point I would ask you to pause the video and solve these simultaneous equations by yourselves. Okay. I hope you are able to solve for it yourselves. It's a simple system of linear equations. So let's see. I won't show every step of the calculation, but show you how it is done. First of all, you can substitute this into that. Okay. From these things we have to eliminate I1, I2 and V1. Okay. So by substituting this into that one, we will get a relationship between V1 and V2. So we will see that we will get V1 to be equal to minus Y22 plus GL divided by Y21 times V2. Okay. Then we can take this one and this one and put it in here. Okay. So, when we substitute this into that, we will get Vs minus V1 times Gs equals Y11 V1 plus Y12 V2, and we can substitute this one into this to completely eliminate V1. And if you obtain the final expression, you will see that V2 by Vs will be equal to minus Y21 Gs divided by Y11 plus Gs, Y22 plus Gl minus Y12 Y21. Okay. So, this is the expression for the voltage gain, and you can also from this make an expression for power gain, which will be related, but of course little more complicated than this. The output power will be V2 square by RL, and the input power, the available power from the source, which has a source voltage of Vs and a source resistance of Rs. This is the maximum available power, which you know from maximum power transfer, is Vs square by 4 Rs. You can calculate this. This is the power gain. Now, this expression will be a lot more messy than this. So, I will just maximize this, though our intention is to have a large power gain. It turns out that the conclusions we draw from maximizing this will be exactly the same as what we get from maximizing that one. So, I will stick to the simple expression for now, but you can, as an exercise, try to do this and you will find that you will get the same answer. Okay. So, why did we calculate this? We have some gain, and of course, we would like to have as large a gain as possible, mainly because we are greedy. Okay. I mean, we have a small signal and we want to amplify it as much as possible. That is, our aim is to realize amplifiers, and amplifying by a large amount has lots of benefits. Now, one obvious thing is that you can make a small signal large, but you also know from preliminaries of negative feedback that you have to have a large gain in order to realize an effective negative feedback system. Okay. So, large gains are very useful. So, that is what we will try to do. Okay.